Hi everyone, my name is Mario DiMauro and I'm with the University of Salerno. During my speech, I will present a statistical characterization of IP multimedia subsystem, a well-known network infrastructure exploited to handle multimedia content across mobile and fixed networks. This is a joint work between University of Salerno, represented by myself and by professors Maurizio Longo and Fabio Postiglione, and the Edinburgh Napier University, represented by Professor Antonio Liotta. I will start by briefly introducing the main functionalities of IMS, with a special focus on a container-based deployment realized through Clearwater, an open-source platform allowing to deploy a containerized version of IMS. Then, some recap about the network queuing model chosen to characterize IMS by a statistical point of view. The formal model is then followed by a numerical analysis where realistic data are derived from the experimental testbed. Finally, conclusion and some hints about future research. IMS is considered both by industrial world and by standardization groups as a key framework to manage services such as HD voice or video within 5G networks, but it also acts as an intermediary to guarantee backward compatibility with previous network architectures such as LTE or LTE Advanced. Remarkably, in 2018, an IMS Vault service has been launched by 138 operators all around the world. The basic structure of an IMS framework includes a number of nodes, such as proxy CSCF, which acts as the first contact point with the external world, the serving and interrogating node, here collapsed in a single node, with a double function of message routing and contact point with other IMS domains. The home subscriber server, a kind of database including information such as user profiles, identities, security information, and so forth. And service location function used to forward a request to the right HSS in case of multiple HSS. And this architecture is very common in realistic IMS deployments. Moreover, here you can find some recent references of the authors which are focused on similar topics for who is interested in an in-depth analysis. According to the network function virtualization environment, also MS can be virtualized. Precisely, we consider a containerized deployment of MS where we distinguish 5 layers. The hardware layer or physical layer, which contains all the physical components or equipment, just like CPU, RAM, power supply, and so on. The hypervisor, which acts as an interface between the underlying hardware and the application or software layer. The virtual machine, which is the virtualized environment hosting the whole container structure. The Docker, that is basically a container manager. And on topmost layer, we found the container implementing the software service logic, namely the proxy logic, serving or interrogating logic, or HSS logic, and so on. The containerized IMS setting is realized through the Clearwater framework, whose main architecture is shown in this slide. For our purposes, we model just the main nodes in the core, namely Bono, Sprout, and Homestead, which represent respectively proxy, serving, interrogating, and HSS nodes. Again, some auxiliary nodes such as Homer, that is an XML document management server, or Alice, which exposes some HTTP-based APIs, are embedded by default in the Clearwater distribution. Again, a stress tool based on CPP has been installed on an external virtual machine to simulate a kind of workload stress. In our testbed, we deploy Bono, Sprout, and Homestead on 3 separated virtual machines. In a typical IMS framework, it is easy to recognize a service function chain structure where each node is connected to another node in order to provide a specific service. Such a topology inspired us to exploit the queuing network formalism to characterize the IMS chain from a statistical point of view. Specifically, each node can be modeled as a queue with arrival rates indicated by lambda and service rates indicated by mu. In particular, the containerized IMS can be modeled as an open queuing network. That means that all the processed IMS requests are not reinserted in the system once they are processed. This kind of network can be described by the so-called balance equation, where lambda I represent the internal arrival rates, namely the arrival rates at the intermediate stages of the network queuing structure. Lambda is the external arrival rate, namely the arrival rate at the PCSCF node. N is the number of nodes. And PJI is the routing probability, namely the probability that a job or a request is transferred to node I once service at node J is completed. If we assume that each node can be modeled as an MM1 queue, a very common assumption in this field, we can apply the Jackson theorem result, allowing us to express the join probability vector as the product of marginal probabilities of having key I requests at node I. Again, an extension of Jackson result known as BCMP theorem allows to also differentiate the classes of requests. And this latter result is useful to model, for example, quality of service scenarios where more classes of jobs or of users or of requests are possible, for instance, gold, silver, bronze, and so on. So in summary, we have two scenarios, the single class scenario and the multi-class scenario. This distinction will be useful for the forthcoming analysis. To quantify the performance of IMS, we need a performance metric. We start from the mean time spent by an IMS request within a node that can be seen as the sum of mean time in queue and mean service time. Accordingly, the overall performance metric is the total mean time spent across the whole chain. Once defined as such a performance metric, we want to solve an optimization problem aimed to minimize the mean time spent in the IMS chain, where to each node can be assigned hardware resources embedded in a capacity factor, CI, and where a budget or a cost constraint, C, has to be taken into account. So the question corresponding to such an optimization problem is, which is the optimal distribution of capacity factors among nodes, useful to minimize the mean time spent across the whole containerized IMS chain given a certain budget constraint? Well, we solve numerically such an optimization problem where parameters such as mean service times of nodes are directly derived from our experimental testbed based on clear water. The solution is a set of possible IMS configurations where capacity factors CI are differently distributed among the nodes. In this table, we report some exemplary configurations, 4 configurations, where the number close to each node in the first column represents the capacity factor, whereas in the second column we have the performance metric result. The first line contains a kind of dummy configuration where capacity factors are all equal to 1 for each node, summing up to 6. The following configurations, namely lines 2, 3, and 4, instead are all equally priced with a total number of capacity factors amounting to 18. The difference lies in the distribution of such factors. Precisely, configurations 2 and 3 have asymmetric distributions, whereas line 4, configuration 4, has a well-balanced distribution of capacity factors, all equal to 3. The result is that the optimal configuration is the last one, since it minimizes the mean time spent across the chain, the IMS chain, and amounts to 0.0077. Let us now consider an additional analysis. Well, if you remember what I said some slides ago, it is possible to model a single class scenario obeying to classic Jackson theorem or a multi-class scenario through the BCMP extension. In this slide, we summarize two scenarios that we want to compare. In the single class scenario, on topmost part of the slide, we have two HSS nodes, each one managing two separate classes of users, precisely for user equipment 1 and user equipment 2. In the downmost part of the slide, we can see an example of multi-class scenario where we have a single HSS able to manage simultaneously two classes, class 1 and class 2. So in this analysis, we compare such two scenarios through the mean time spent in queue by IMS requests as the interarrival times grow. Red curves refer to single class scenario, whereas black curves refer to a multi-class scenario. In order to have a fair comparison, we study the behavior of the mean time spent in queue when the same couples of probabilities values are assigned to the occurrences of classes 1 and 2. So here we see a couple of probabilities equal to 0.4, 0.5 for class 1 and 2 and for the two scenarios. Whereas here in the rightmost part, we see another couple of probabilities values 0.3 and 0.6. Again, here we can see in the leftmost part another couple of probabilities 0.2, 0.7, and finally 0.1, 0.8. In all comparisons, we can see that black curves always stand up with respect to red curves. And in particular, the main trend we can observe is that red curves span over a large interval of values, indicating that the single class scenario, in a sense, offers more flexibility with respect to multi-class, namely the black curves. And this is absolutely reasonable, since in the single class we have two HSS nodes that can react differently according to the load of requests. By contrast, in case of a single HSS node, a request belonging to class 1, for example, has to wait its own turn in case the request belonging to class 2 is being processed. Obviously, the flexibility of single class scenario with two HSS is paid in the coin of a more expensive setting, since an operator has to buy two HSS in place of just one. So, in conclusion, I've presented to you an IP multimedia subsystem infrastructure deployed in a container-based environment thanks to an open source platform named Clearwater. Then I've presented to you a queuing network formalism that we adopt to capture some statistical properties typically expressed in terms of mean response time. And finally, I've presented a numerical analysis where some realistic parameters have been derived by our experimental testbed, just like service rates. And such analysis has been split in an optimal configuration analysis and a comparison between single and multi-class scenarios. Actually, we are working along several directions. Two in particular. The first one is to extend our performance analysis to a performability analysis, where beyond the performance metric, we also consider an availability structure of IMS, where we are also interested in guarantee, for example, some degree of availability, for example, the 5/9 of availability. That is a typical metric used in the data center or in cloud environments. And again, we are working on a generalization of our queuing network formulas to different service function chain structures that exhibit more or less, such as the containerized IMS, a chained structure with a particular interconnection among nodes. Thank you for your attention.